Hi everyone, welcome back. Yeah, so why don't we kick off? Ruben, you looked into this point about the UCT and Potter's theorem and the justification for a particular step. Do you want to maybe just jump in and say a few words about that, what you found?
Yeah, so basically, I mean, the way I did it was you can write part of the sum as an integral, and then Potter's theorem basically allows you to use dominated convergence. And then it just turns into an integral of like 0 to 1, the integral of t to the minus alpha from 0 to 1. And that gives you basically what you need. I ended up looking at the proof of Karamata's theorem in Bingham, Goldie, and Twiggles. And they have the integral version of the result you say. Well, I noticed that a lot of the results you cited were like discrete versions of their versions, because they would write it in terms of an integral, and then you would use it in the case of sums, but they basically had that exact same result.
Oh, are you saying there's a slight imprecision in the way we cite their work then? That it doesn't actually perfectly?
Well, I recall you cite theorem 1.7.1 or something, and I mean, it might be trivial because it's just a sum, so maybe just take the measure space to be some discrete space, but I didn't directly see. I mean, it's probably not a big deal.
I see. Oh, okay. Well, we can maybe.
But it still held. I mean, wasn't that much trouble.
No, okay. Right.
I'm curious if did anyone else do it? I mean, a more hands-on way, because I didn't end up using the UCT.
Did anyone else have a look? No, no, it seems not. Okay. You can show if you want. You had a page you're working, right? If you want to share it.
Yeah. Let me bring it up. Oh, I don't know if I can't share my screen right now.
Oh, I'd have to make you a host.
Yeah.
You're a host. Let me see if I can do that. Oh, well, I don't actually see where is the option for making, Milan, do you know how do I find the option for making Ruben a host?
You can just, so on share screen on your screen, you should have, there should be a little small arrow at the corner of the share screen button. And then you can say allow multiple participants to share or something, and that will allow them to share.
Try now.
Can you guys see that?
Mm-hmm.
Yeah, so I mean, lemma 1 is basically all the hard work, which is not really that hard, but yeah, so you just divide it out, and then equation 1 is kind of the crux, is just rewrite this sum as an integral from 0 to 1 of kind of this indicator function times a function that tends pointwise to x to the minus alpha. And then Potter's theorem allows you to bound that because alpha is between 0 and minus 1. So you can bound that by a function that has bounded L1 norm. And then basically you just take the limit. And then.
Mm-hmm.
But I think I might have the actual proof. I looked it up and their proof was almost identical for the integral case. I think this is it. Yeah, this is basically it.
Yeah, okay. So the only distinction is that's an integral rather than a sum, is that right?
More or less, yeah.
It doesn't actually use the UCT, just Potter's theorem.
No, they didn't use it either.
Mm.
And then I don't know, the theorem 1.7.1 I was talking about might be a bit ways down there. Or I don't know. Let's see.
There it is, yeah.
I mean, I didn't see if they're obviously equivalent. I just noticed that.
So equivalent to a sum expression being the same as an integral, which is, you're saying a slight logical gap in what's written, that there's a sum that should be an integral in order for this result to be applied.
Yeah, but you might just be able to take a function that's kind of a step function with values.
Yeah.
Being the sum, which I don't know, probably should work.
I see. Well, okay, yeah, that's worth mentioning, and maybe we can review that point. If there's a slight gap there, then that would be helpful to check out. I guess it's in these kind of classes and situations where one discovers these little gaps. Well, Jan Lucas and Anton had a different route for discovering a bit of a gap in this work, but we'll hear about that on next class. So what I'll do is, thanks for that, Ruben. What I'll do is share my screen now, and then I've written a short review of where we are, just as people were coming in. The two propositions that are obviously backdrops for the whole framework of the main result of this paper are recalled here, that we have this first proposition in which the measure mu is assumed to have this condition on its GDC of its support. And then we have this characterization of the extreme or Gibbs measures according to whether the geometric aspect of the random forest, does it have just one tree and everyone joining together, or does it have infinitely many? Almost surely, in the first case, we have these two trivial Gibbs measures and nothing else for the extreme or Gibbs measures. And then in the other case, we have this nice one parameter family. We've been studying the lambda p with the colorings of the trees going on. And so proposition 2, we proved that, proposition 1. Proposition 2, we are in the middle of proving, and that says that mu is in this class of heavy tail with this regular variation for some alpha positive. And it says that if alpha is bigger than a half, then the forest has just the one tree, almost surely. And if alpha is smaller than a half, so you have somewhat greater capacity to make fast jumps, then you have the forest structure almost surely with the infinitely many trees. So we're in the midst of proving that second proposition, and a tool for doing that has been this lemma that we've already proved that says that that's Qn being summed there. So if alpha is positive and mu is in this class, then the sum of the first x of the Qn terms is behaving like x to the alpha up to this regularly slowly varying correction. And then as for the sum of the Qn, the sum of the squares, rather, that's infinite or finite, according to whether alpha exceeds a half or is less than a half, with the case of being exactly equal to half not being addressed. No doubt there would be the usual, business about when you integrate 1 over x and start putting log terms in the conditions that ensure convergence, or otherwise would probably be relevant if you studied that. So yeah, we're pretty much home and dry actually, given this result which we have proved to give the proof of the proposition. So I'll just ask for questions before I get underway with that. Any queries or comments before I start the proof of prop 2? If not, I'll just go ahead. Okay, so recall that indeed we have alpha positive and mu in this heavy tail class, a more or less heavy tail class. So if I take two integers, with n being the smaller, we're interested in the condition, conditions to ensure that these points meet almost surely or manage to stay apart. almost surely. What we want to show is, WTS want to show, is that when n and m, when alpha is bigger than a half, that's the case where we're supposed to just have everyone joining together, and that's represented by the statement that these lie in the same component of G mu with practical certainty, with probability 1. Okay, obviously, if that's true, then we can use a countability argument to show there's just one tree. Okay, whereas if alpha is less than a half, then there's a positive probability so the positive probability will depend on the difference between n and m, and the view will be that when n and m are large, the difference is large, then the probability will be approaching 1 of escape. So if you take n and n plus 1, in this case, the view is that there'll be some local moves going on that will largely determine if the characters manage to hook up with each other, and if they don't, then one of them will take a big jump after a while, get a long way away, and after that point it will be unlikely that they succeed in meeting. That's the flavor of that case. So R mu, remember, is this, I won't write it out again, but I'll verbally recall that it's this system of partial sums. It's the places we land in the hopscotch game, in which we take independent jumps according to the law mu, and we include 0 in the set, I think. So let's take independent copies of this as a tool for analysis. Okay, so it's easy to see that n and m lie in the same component of G mu, almost surely, precisely when our independent processes. Okay, so what I'm going to do is these renewal processes kind of naturally, in terms of their just internal definition, run forward in times, but in our actual application, we're concerned with the ancestral line. This is a statistical copy of the ancestral line that emerges from n. So the jumps go backwards according to mu to the father and the grandfather and the great-grandfather and so on. So what I'm doing is taking, in fact, two statistically quite independent copies of the ancestral lines emerging from n and m, and I'm asking the question whether the mean number of intersections between those is infinity. So the processes being considered here in this equation I just wrote are not precisely the copies of the ancestral lines that we see jointly in the process, in the sense that in the actual process, when things hit, they will stay together. So we won't actually have independent ancestral lines, but it's a technique of proof. It's a convenient thing to do, to consider statistically independent copies of the ancestral lines. And then, as I say, it's easy to see that if these processes are definitely meeting the actual real deal processes, then these idealized independent ancestral lines will meet infinitely often. And so the mean number of times they hit will be infinity. Does anyone want any clarification on that equivalence, which I've not been very precise about? If the things meet almost surely, then I think the view is that the independently realized things will in fact meet infinitely often, almost surely. So that would certainly imply that the mean number of times they meet will be infinity. I suppose I should really go the other way. So I would try to convince you that if the mean number of times they meet is finite, then I want to argue there's a positive probability that they don't meet. Is that the right way around? No, I don't think that is the right way around. The contrapositive is that if the mean is infinity, then they Is that right? I want to argue it. If the mean is infinity, then they meet almost surely. Well, anyway, I don't know. Is that right? if they have positive probability of not being in the same component, then it's certainly true that then I want to argue that the mean is finite, I think, and for that, it's certainly true that there's a positive probability that the set is empty. If the set is non-empty, then the view would be that, I suppose, having got the things to meet, then perhaps a finite trajectory that might possibly happen after they meet for the first time, I could guide them back into their original relative positions, n minus m difference with a finite sequence of moves that could happen with positive probability. And having got there, they would then have a positive probability to not meet. So each time you come back and score a success, there's a positive probability of never meeting again. So that creates a geometric structure for them, total number of meetings in a finite mean. That's the reason that this equivalence is true. Okay, and then we can do some other kind of a moreover statement that n and m are general here, but it's equally not very difficult to see that the existence of a pair n and m with the mean being infinity is equivalent to all pairs having that property. One direction is obviously trivial. The other direction, I suppose, I think it's just a matter of guiding things in. If you had a particular rather special n and m for which the mean was infinity, then if I took another pair, even at much greater distance, there would be a positive probability, depending on that difference, of guiding in the motions to be at the very specific difference that is the one that gives the infinite mean, and then you would feed off of that. So with positive probability would come in, and then you would enjoy the infinite mean. So that would deliver the infinite mean to the generic NM pair. Okay.
Does that step need the GCD property?
Yeah.
To end up at the same place or something?
Yeah, indeed, that's exactly right. Yeah, when you take these sort of finite number of steps guide you into a relative difference that's a specific value, yeah, you do. And indeed, I think if you just take an example where the mu is delta 2, so you jump back 2 steps, then you see if you're in the same parity class, then you meet infinitely often almost surely, and if you're in the opposite parity classes, you never meet almost surely. So, this is a genuine phenomenon. Yeah, that's right. So that just gets us, allows us the luxury of focusing on a particular choice of n and m, really. We can take 0, 0. There exists exactly one component of G mu if and only if the mean value of, I'm just taking, I think, n and m equal to 0, and then maybe I'm harmlessly working rightwards rather than leftwards in what I'm doing here. There would be silly minus signs attached to both R expressions that can just be dropped by the symmetry of the flip symmetry through 0. So yes, sorry, this is equal to infinity. I guess that means almost surely there. We know from an earlier result there's a dichotomy that either there's one component almost surely or there's infinitely many. So we're just distinguishing between those two alternatives, and this alternative, in which there's just the one tree, is characterized, we see, by this condition. And this condition is nice because, of course, we know, don't we, what the value of this mean is, right? What's the value of this mean in terms of expressions we've been seeing in the class? Well, it's infinity, but I don't mean that. What is it in terms of parameters or quantities that we've introduced in the class.
I believe that's the sum over the Qi square.
Yes, that's right, isn't it? Yeah. Yeah, so yeah, Lucas is right. This is the, are people comfortable with this? It's, you know, hopscotch games are being played by a girl and a boy beginning at 0, and they take their independent mu jumps. So how many squares are there that are visited by the boy and the girl? Well, it's the sum over each square, the probability that that square is thus visited. The probability of it being visited by the girl is Qn, and the probability it's visited by the boy is Qn, and the choices are independent because the boy and the girl jump independently. So Qn squared, the probability of having a cross level n and summed up over n. Technically, we include 0 in the sum, and that's contributing 1. Yeah, okay, so then that's pretty much done and dusted at that point, because then the result follows from the lemma, part 2 of that lemma, which said that when alpha is less than a half, this sum is, whichever way around it is convergent. Let's see, I think so. When alpha is less than a half, and that's right, it's convergent, reflecting the big jumps, possibility of getting away. And when alpha is bigger than a half, it's divergent. So that is the characterization that we've identified in terms of whether or not we have the one component almost surely, or the other possibility of infinitely many components almost surely, in which is characterized by this sum being finite and implied by the condition that alpha is bigger than a half. Okay. So yeah, the two lemmas have now been, the two propositions have now been delivered, and we are building towards a treatment of the actual walk we define. You know, we sample a lambda p extremal Gibbs measure in a regime in which such things exist, where alpha is, I have to torture myself again to remember the condition on alpha. Alpha is between 0 and a half. In that regime, the lambda p measures exist. So then we have x. That's a map from z to it's the assignation, the random assignations of -1 and +1 according to the law lambda p. So just recall the framework. We then let S be our walk that's at 0, 0, and then its increments are given by the x process. So recall that Sn is the object of study, really. It's the object that we try to scale to take account of its drift and diffusivity. That's the right word, drift and variance, in order to be aiming to capture a sense of a scaled coordinates and a limiting process. So S, I can write for emphasis, S is coming out of the measure lambda p, you understand, and then N is perhaps rather high, so T develops the quality of a continuous variable. Maybe there's some silly integer rounding that's needed to make sense of this. Let's ignore that. So we have the notion that you know, it's a p 1 minus p minus 1 type situation. So 2p minus 1 is the net drift. So we cancel all that away to have a centered process. And then we, the view is that the standard deviation will be behaving like n, the power law behavior will be n to the half plus alpha. So we divide through by that. and then further take account of the slowly varying function that is, of course, emerging from the definition of mu. Yeah, okay. So, all right, we want to, the next step is anyway a lemma that builds towards okay, so in the first instance, so this is a scaled process, and we want to say it statistically settles down in some sense to this fractional Brownian motion with Hurst parameter alpha, or is it a half plus alpha? Whatever the Hurst parameter is, I think a half plus alpha maybe. And now there are different topologies and sense in which we can claim such convergence. The first step will be to claim that this is true in finite dimensional distributions. That's the acronym for that. Just study statistics at a given finite collection of times t1, t2, t3, and to understand what the limiting distribution in law of this coupled system of real random variables is that are the marginals of this process. After that, we'll want to boost towards a stronger form of convergence that was stated via couplings, or it could be via weak convergence with an appropriate locally uniform topology, and that will be something that Anton and Jan Lucas are perhaps going to touch on in the next class in their presentation. So in terms of an understanding that we have a Gaussian process and its finite dimensional distributions, we're particularly interested in understanding the basic statement that the object is Gaussian in its increment, and understanding the size of that increment. So the next lemma is doing one of those two pieces. This is lemma 3.1 from the paper, and it says, so the variance of the walk Sn, so I've changed the notation slightly here, I suppose. Maybe you understand that mu is given and it gives rise to this whole structure. The extremal gives measure lambda p, which goes on to specify its realization x, and then Sn is the sum of the x1, x2 up to xn, okay? That's what Sn is. And then we have a nice formula for its variance using the tilde notation. So the left and the right-hand side are deterministic functions of n, and n rises to infinity. The claim is that the ratio of the left and the right-hand side tend to 1. That's what tilde means. And so I have a particular formula here that we worked out. Yeah, so the growth rate in the formula, and the thing to focus on as the individually most important term, is what I just wrote down, n to the power of 2 alpha plus 1. So remember, if alpha is 0, you have ridiculously big jumps in a sense of absolute escape. And that's making reference and contact with the independent discrete white noise case, in which the field is plus or minus 1 independently. So then you would have a kind of a Brownian behavior. So alpha is 0, the variance is linear in the Brownian case, okay? And then it only rises from there as alpha rises. Yeah, and then I have the ln correction coming from, as always, the slowly varying term appearing in the specification that mu is in the function class gamma alpha. And then we have some other quantities that I haven't defined yet. The other thing is a constant, but the constant depends on, I suppose, two quantities. One is the notation for this. So in general, what's written with the 0 is a special case. This is a Fourier coefficient for absolute value of q squared. Explicitly, this quantity is this one. Okay, that particular sum is the ith Fourier coefficient of this function, absolute value of q squared, capital Q is the Fourier series for it's the Fourier transform of the Q series. Anyway, it's defined simply by that expression that you see, that sum expression. And then there's a particular expression for Q alpha, which I will record. I'll do this lemma at a high level of detail. I'll drop down to a lower level of detail as I summarize the reason we have the finite dimensional distribution convergence, I think. But, so let's do this reasonably carefully. So I'll tell you what the constant is. It's a raised to the power of -1. Can I squeeze it in? The gamma function evaluated at 1 minus 2 alpha, gamma of 2 alpha, the cosine of pi alpha. Well, okay. It's only have so much interest, I suppose, unless we can interpret terms. But anyway, there's a given constant dependent on alpha. So let's look at the proof. I will, maybe the order is slightly strange here. When we reach the end of the proof, I will give an alternative, a kind of heuristic for why we see the power of 2 alpha plus 1, which is what feeds into the Hurst parameter alpha plus a half, I think, of the resulting fractional Brownian motion. But for the time being, let's work rigorously. So we have a collection of trees that intersect the interval from 1 up to n. The trees of the forest G mu. That intersect non-trivially this integer interval, okay? These are ones that are going to play clearly a role in relation to Sn, in the sense that the variance of Sn is 4p 1 minus p. That's a kind of classic variance expression you see in relation to Bernoulli random variables of parameter p. It is the variance of such a random variable, I think. So what is happening is that there's a sense of squaring the intersections. That is the number of vertices that lie in the ith tree in the interval from 1 up to n. So if I square that, because there's a sense of a coin flip then, right, on those guys. As they get flipped, plus or minus 1, with probability p stroke 1 minus p. And so the variance arising is this expression, which is then summed over the trees that have the non-empty intersection. People comfortable with that? So this can be written as a mean of a double sum over vertices in the concerned interval of the indicator that I and j lie in the same tree. Simply because if you think about the classification of the interval 1 up to n into its trees, and you'd say there's a particular tree that has intersection k there, then the number of pairs I and j that lie in that tree is k times k, which is reporting the correct value, the square of the tree intersection for that tree. And then obviously we sum up over the different trees that intersect in order to have this expression. Yeah, so then we can just, of course, pass that mean through. We are dealing then with the sum over the concerned pairs of indices of the probability that the two indices lie in the same tree. So I could write the probability of the event that I and j lie in the same tree, but we can write that differently in terms of the notation that we have. When do I and j lie in the same tree? Well, it's when the ancestral lines that begin at those respective locations meet. So if my notation then is for the ancestral line that emanates to the left from I and from the left from j, do they actually meet? Okay, so quite a nice expression for the variance in a way, but something that we have to analyze in terms of course, this probability that's just been written down. So one thing that we can analyze a little more directly that's somehow a close cousin of that probability is the expectation of the number of meetings. So yeah, now I think here I may be a little bit abusing notation. Let me just write down what I've got and then we can review it. So I have my two indices, and I want to say that the mean number of intersections between the ancestral lines is equal to this sum. So it seems to me that that's true only in the interpretation that AI and AJ are actually independent ancestral lines. So we have our ancestral line coming from I, or indeed from J. It has a perfectly clear law, the hopscotch game running to the left with the jumps mu independently taken. We have a coupling, of course, of ancestral lines coming from the model, in which if there's a meeting of the ancestral lines, there is then a coagulation and a joining together afterwards. I think it's an abuse of notation. I don't know if it's also in the paper. It probably is. I suppose that's where I got it from. I think what's meant here is that the A and IJ are not, in fact, enjoying the coupling relationship they have coming from the actual model. They are simply the idealization we already saw in this class, in which I and J are just independent copies of the ancestral lines run from these starting points I and J running to the left. Okay, that's the only way I think you could hope for that formula. A formula that we've already analyzed, at least in the case when I was equal to J, and I was talking about the boy and the girl. The boy and the girl now jump from different starting points, and then this counts the probability that the various places they could be meeting, that they do meet, if they jump independently. Okay, so we have to accept that that may be, it might be a little imperfection in the way we wrote up, if that's the case. But anyway, I hope that's clear with the independent formation. So this then is just notation, which I haven't thought very carefully about these Fourier interpretations. It's just, to some extent, can be considered to be a kind of abstract notation, if you like, that anyway, it's just a notation for this sum, I think, largely. So that's okay. That's at the level of the mean, but I think there's a different perspective on this mean that is going to allow us to actually address the quantity that interests us, which is the probability of meeting. So let's take a look at that. So a different perspective is to say that the mean number of times the independent guys meet is the probability that they do meet at all. This is in the independent formation, as I say. Now, if you've got them together, the view is that I suppose you could form them independently, but in a particular order, where the one that's, you know, they formed up to a particular point, and then you make the one that's further along on the right jump first, and then, you know, that iterates. And then you check if there's a time when they land on the same spot. And then have a bit of a think about what's happening from this point. I should have a I should have a not empty. So, okay, that's what I mean. Form them in that way and then check if they meet. If they don't meet, then obviously the mean is 0. So if they do meet, we need to have a bit of a think about what the conditional report to the mean value is. And you see, that's just the, well, it's just the mean value given that I and J are both a given value such as 0, right? So we've seen that already what that sum is in this class, right? That is the, this expression, okay? That's the conditional mean given that they meet, or equivalently taking I and J equal to 0. well, yes, all right. So that I don't abuse notation, I'll write a K there. Right, so that's good because that introduced the quantity that we're interested in, the probability that the lines don't meet. So if we go back to, I may have used the information, my notes say I used the information that Q of 0 is 0. Perhaps I did use that. What we learn from that is that the variance of Sn, if we were to glance back, let me just write out the formula and maybe we can glance back. Q squared of 0 is just a notation for that sum. You see the sum of the squares, okay? And then we have this. So let's perhaps just glance back at the formula we had for the variance and just see what's going on. So I've got the variance, it's quite a simple formula in a way. It's 4p, 1 minus p, and then the sum of these probabilities. So what I'm doing is, I've got those probabilities right there. So I'm going to be replacing that sum and by the ratio of this mean you see, and then downstairs we'll be seeing the sum of squares. Well, downstairs, that's what's the Q squared 0, okay? So then what you're left with is the sum and should be that mean, but then that's the information here. So that's the Q squared J minus I, so that's perfect, right? The only thing is in the paper, it says at this point, it writes absolute value here. I guess that they are equal, aren't they? That's right. If you look at these expressions that you have here, then I think they are equal if I replace J minus I by I minus J, because it's just an irrelevant, it's just an ordering thing, I think. So, all right, we've got that formula then. So then what we can do is have a bit of a rewrite of variables. So I've got 4p, 1 minus p with this same denominator. And then what I'm doing is, what remains, I have a double sum here, but it's all expressed, the only active variable in the sum and is the difference. So we can reduce this to be a single sum by summing over level sets for J minus I. So what we have is that 2 is probably a symmetry factor according to whether I or J was greater. And then what I'm writing here is I is going to be a relabeling of J minus I. Okay, so you see how many times could I get a given value of I as a difference of J minus I, reuse of I, J minus I, well, I and J are between 1 and n. The number of times is n minus I. You can think about the extreme cases to check that. And then you have a diagonal case, which, yes, I suppose the diagonal case was separated because perhaps there's not the symmetry factor of 2 in that case. I have n q squared at 0. Okay, so yeah, so of those, the dominant term is going to be the first one. The diagonal term that I just wrote is going to be insignificant because it only grows linearly in n. Q squared 0 is just a constant. So I have a linear growth in n, but we're anticipating growth of the form, I think, n to the 2 alpha plus 1, that's what we're anticipating. So we expect the other term to dominate then if we sort of jump ahead to some extent. And indeed, it suffices to show that this term bears the requisite burden in order to have the lemma as stated. So this is for the particular k alpha constants that I mentioned, the what we'll be seeking, let me call that the cross relation. I'll be proving that, and that's what suffices. So the dominant behavior here is n to the 2 alpha plus 1 with the correction coming from the slowly varying part and the further constant on top of that. Okay, so we want to gain an understanding of these Fourier coefficients of the square of the Fourier transform of Q. So we can unpick this in terms of what we know, what we learned in a previous lemma on the basis of the information that mu lies in the tail class gamma. Alpha is an understanding, if you recall, do you remember that business with there was sort of a real part and an imaginary part, and there was something like a cosine and a tangent going on, and then we added up the squares of those to obtain a slightly simpler piece of information. Well, the piece of information we obtained at that moment was this one. So t here is close to 0 when we write this. This is the Fourier transform of the p sequence that's at stake. That's the capital P function. It is approaching 1, and the rate at which it does so is indicated here, alpha being positive after all, and t, as I say, being close to 0 here. So q is, for both the Laplace and here the Fourier side of things, in this relationship with P. Okay, that's the transform of the Q sequence, capital Q. So naturally we have that, I'm just going to be writing down the same thing with reciprocals now. Behavior continues to be close to 0. So I square that up because that is the coefficients we are seeing are appearing in the Fourier transform of the square of the, they are the coefficients in the expression for the Fourier transform of the square of the Fourier transform of Q. And so I'm just squaring this up. So I've got t to the minus 2 alpha at this stage, L 1 over t to the minus 2. So now we have another, I assume it's just probably one of the results we've already seen as a Tauberian theorem. It's from the text BGT that Ruben mentioned, for example, at the beginning of the class, the theorem 4.10.1a. I didn't really check this preparing today, alongside the information that this is real. I frankly didn't think carefully about this, but it seems in line with the types of results we're using to transfer information about the behavior, and in this case, I think blow up of a Fourier transform near 0 to the coefficients of the associated series and how they behave as n here gets large. So I take q squared I, and then you have these kind of relationships. So it's a bit boring to write out all these gamma functions, but they're being introduced by these Tauberian theorems alongside the ones we already have. Do we have any at the moment? Well, I don't know. Anyway, I have this coefficient. So I have n to the 2 alpha is the thing to focus on. It's just the same as here, right? 1 over t becomes n, okay? And then coming along from the right is ln to the minus 2 over 2 alpha. Okay, it's a bit gory to see all the details, and since I haven't really explained the proofs of these Tauberian theorems, I suppose it's a slightly empty exercise at one level, but okay, I am keeping track of it. So the actual expression that we are concerned with in our context is displayed at the bottom of this page, and obviously it's a close cousin of the types of expression that we've just seen, where I have just this pure sum. So I just now want to move this over with, I'm just writing the same thing down to get what I want by introducing this factor of n minus I, q squared I gets summed from I equals 1 to n. That is the object that we wish to understand the asymptotic for. So it's broken into two pieces really, according to that n minus I. The first one is just n times what we have right here. So I'll just be writing down this expression with the power being 1 plus 2 alpha, which by the way is the type of power growth we're anticipating. And then I have the other term where I'm subtracting I in this more dynamic way. So that will end up looking more like an integral expression that is riffing off the basic information that we have here on this page. So yeah, all right, so I have this Pauling constant that I force myself to write out quickly again. 2 alpha cosine pi alpha. Hopefully that's the last time I write that, raised to the power of -1. Then I have the fundamental growth rate with the correction. Okay, so the first term is just, that's what it is, period. If I stop writing there, I would be dealing with the n times, but I also have the minus I. So what's happening is, oh, that's not 100% true, actually. There is another term. There's another factor. Anyway, let me write this integral. So why am I seeing this integral? It's to do with the way that, well, I suppose in the first instance, I'll just focus on, you see a 1 minus x there in that integral that is playing a role counterpart to the n minus I in the discrete sum, okay? So the 1 represents the n. So if you just look at that 1 and forget about the other part and integrate up what it multiplies, you just return 1 over 2 alpha, right? If you can eyeball that, that's what that integral is, without the minus x being present. So I assume that corresponds to, yeah, well, that corresponds to the 2 alpha that appears, I suppose, here, right? So this reports the correct answer if you didn't have the minus I up top, because I've done nothing other than multiply the expression here by n to report this, in the sense, as I say, the 1 over 2 alpha downstairs is the integral coming when you don't have the minus x. So the minus x is coming in because you're doing a trick that maybe is similar to what Ruben was looking at. That, I mean, I is n times I over n, and I over n is becoming the continuous variable x. So when you integrate that, well, that's the reason for that. Then we actually have to perform this integral. So it's 1 over 2 alpha, and then the other one is x to the 2 alpha is being integrated to yield this. So this is simply equal to, I think, the product of those denominators. Okay, so then that's just what we had. I mean, you're not going to be able to remember what k alpha was, but it is, that's what it is. Somewhere. Two alpha times 2 alpha plus 1 in the denominator, and then the expression I don't wish to write again in the numerator. Okay, so I guess that means that we've done that. We have done that. Okay. So that's a box on that proposition, the second proposition, really. So we're in pretty good shape in the build-up. Oh, no, that's not a box on a proposition. Sorry, that's the box on this lemma 3.1 that tells us a formula for the variance of Sn. That's what we just did. So yes, I'm tempted to now give a bit of a heuristic overview of why that result is actually true. In a way, it's a slightly strange order to do things in. It is my hope with this topic to be a bit more participatory about it. So we've had some discussion about these cookie collector models. I also have some hope for a voter model. Well, there's a couple of directions, including a voter model counterpart to the model, the Pavlov-Pugliese model that we're studying. And so in a way, what I want to do is not be too fixated on a particular method of proof of things, but to back up and think about the intuition for why the growth rate of the variance of Sn is what it is, n to the 2 alpha plus 1, because I think that that's a more robust approach in terms of beginning to examine other problems. So I do want to give you a bit of an informal view of this, even though I've, in one sense, done my job, in the sense we've already proved it. but a little bit of intuition perhaps as well would be nice. So yeah, not being very precise about the meaning of the symbol, you know, but you know, why is this the dominant order growth rate for Sn? So so the informal of this, the relationship between this and tree sizes in the integer interval 1 up to n, or maybe it's 0 up to n. Okay, so recall, of course, that mu is charging this tail in this manner for L, a slowly varying function. So let's just think in pretty concrete terms about the kinds of hopscotch game that gets played over a large number of steps. So if n, let's say capital N steps of the hopscotch game are played and the ancestral line is being formed, how far do we expect to go? So this is, at least if alpha is small enough, I think the relevant condition is that it be less than 1. This is the heavy tail situation, which is so important in this class. It's the reason that we see one of these random devil staircases, at least from my ID sequences, is that the phenomenon I'm about to recall is indeed what's happening. I think we've mentioned it before. The biggest step, if you take n steps, the biggest step, as well as the total distance covered, you know, just how far did you move in your hopscotch game, the little boy and the little girl, the total distance traveled. Well, you know, what is the basic order of this? Well, if we just call that its order n, little n, what's the relationship between capital N and little n? Well, the view is that, you know, there's chances all the time of getting nice big jumps. So the biggest jump you're going to get, you've got probability 1 over n to get it. But the probability at an individual stage of having a jump of order n, you see, that's the same thing as saying that the value, at least at a crude level, to say that the order of the jump is n, and what's the probability that happens, you know, what's the probability it's between n and 2n, that's the same order as saying it's at least n. So, you know, the guiding probability is this, right? Because that's the tail of the mu sequence, the probability that the sample is bigger than n is behaving like this. So n then is it n to the alpha? But more relevantly, I think it's, I want to write little n is n to the 1 over alpha. So, you know, I'm taking n moves in my game of hopscotch. Let's do it backwards. And nice big jumps come along. I take n steps. So the distance I get to from the beginning, if that's 0, then the size of this is n to the 1 over alpha. So this is in the phase here, so this is superlinear growth. And this is also this is dominated by the biggest jumps we make. The 2 or 3 biggest jumps explain much of the distance we move. So these are also of this size, the big ones. There's other smaller ones as well. Okay, so, all right, so let's now change perspective slightly and say, to go out to distance n, and I'm now going to change notation and use little n. So, you know, if I start at 0 and I think maybe about kind of a phase between n and 2n here, okay? So the number of steps needed to kind of get into this phase is number of hopscotches needed is behaving like n to the alpha here. So this is you know, alpha is less than 1. So it's a sublinear number, but the relationship is dictated by this relationship we've just seen, okay? And so this is a justification for why this is the number of steps that's needed. So then on that basis, we can do an informal computation of how Qn is behaving. So Qn, that's the probability that the hopscotch hits n. And I'm being here, I hope it's not practically confusing. It is technically imprecise because maybe it's minus n because I'm going backwards, but who cares, right? I'm going to call it size n. Okay, so the probability of hitting, and this could be n or it could be any point between n and 2n I'm talking about here. So we can now compute this because the point is that well, not very to scale, but there's n to the alpha steps that get made as you travel through the entire region between n and 2n. All right, so what's the probability of hitting a given point? Well, assuming a certain degree of regularity, the chance of hitting one point or another in this phase from n to 2n are much of a muchness. So you've sailed through and hit n to the alpha points out of a total of n, right? So that means the probability of hitting a given point is this, okay? So now let's look at, that's information that can go into having a look at a sum that we've already seen. I'll call it kappa. Let's look at, or related to things we've seen, and we probably have seen it, yeah. So let's look at this type of sum. So what you're doing here is a hopscotch game, and perhaps rather, just the way I do it, I'll have people going forward in time instead. Doesn't really matter, I hope no one's confused. So this is an expression for the mean number of times independent hopscotch games meet when they begin at a distance of n. So this is dominated by, this is intended to be a little bit informal and heuristic. It's dominated by choices of I of order n. The notion is that the number of times we meet in total will be dominated by the phase between 2n and 3n because, well, basically smaller scales than that, closer to n, don't really have the requisite number of points for 0 to swing in and hit them enough. And then if you go further out, then the processes are more likely to have got away from one another and they won't report significant value. So on that basis, we can make an estimate for the growth rate of kappa as a function of n. Okay, because there's n relevant points in this phase where they could be meeting. There's n relevant points, n to the power of 1, but for each one, I want the process coming in from here to hit and the process coming in from here to hit. Okay, so it's going to be a square of something, and it's going to be the square of the probability that the individual process hits. So that's what we just computed, right? Are you happy with that? That's the computation we just did. So the probability of hitting a point out at distance n in the hopscotch game we heuristically argue is n to the alpha minus 1. Okay, so kappa is behaving like 2 alpha minus 1. Now, at least when alpha is between 0 and 1/2, this is much less than 1. And it might be that maybe this computation could go slightly awry in the other case because I was kind of assuming that the processes would get away from one another eventually. For example, in the argument I just presented for why we can say we're dominated by the interval from 2n to 3n. So, okay, kappa, what is it? Kappa is the mean number of meetings of the hopscotch games played from points that begin at displacement n. But in this phase where kappa is small, it's a surrogate for, it's largely the same thing as the probability that 0 and n lie in the same tree. Because the mean number of times the independent processes meet in the case where that mean is less than 1 is behaving up to a constant as this probability, because in order for the mean to report positive value, that the processes have to meet, and if they do meet, they only re-meet on a finite number of occasions. So probability and expectation are the same thing at this level of detail. So we want to study relationships, though, remember, between the variance of Sn and the tree sizes for the intersections with 0 to n. So this debate is permitting me to start making some statements heuristically. What's the mean size of a tree? Let's say it contains 0, but its mean size of the tree's intersection with the interval 1 up to n. So these are the points. 0 is doing its stuff, has its ancestral line. And these are all the points whose ancestral lines will eventually meet 0. That's the tree that I'm talking about. Its intersection with the interval from 0 to n. What size is it in mean? Well, it's a sum over candidate members that are obviously lying on the interval from 1 up to n. What's the probability that 0 and I lie in the same tree? That's what we just computed. It's this expression with n replaced by I. And then this sum is behaving like n to the 2 alpha. So alpha here is in the phase between 0 and a half. So this is kind of intermediate situation where this n to the 2 alpha is growing at a rate n to the something between 0 and 1. Okay, so all right, at some level, what is the number of trees that intersect this interval? It's possible there could be a few trees that come in just once. I'm kind of talking about trees that substantially intersect in the sense of having this order of intersection. So the view is, though, that most of the space is probably, the trees are there's some assumptions going on here. The trees have roughly the same size, but they all should have this kind of size we just computed. So the tree size, when it does intersect, is n to the 2 alpha. So the number of trees involved in order to explain the length of the interval is n over that. So that is n to the 1 minus 2 alpha. Okay, so why don't we then try to compute what the mean of the absolute value of Sn is. So what is the typical magnitude of Sn? By putting absolute value here, I'm talking about a standard deviation, I'm talking about typical size. So what's going on here is each individual tree has size n to the 2 alpha. So that will be assigned a plus or minus 1. And so they'll all kind of contribute on that scale. But then fluctuation will happen at the level of the number of trees. If I take the number of trees and take its square root, I'm working in the case, sorry, where the mean is, let's work in the case where p is a half. So there's no drift. So the mean of the walk is 0. So this quantity I'm recording on the left-hand side here is the typical fluctuation. So the presence of the term I wrote down on the right here means that what's left is just the number of trees and the imbalance in plus and minus 1 assignation. So the answer should be the square root of, in central limit theorem imbalance, of the number of trees. So that is n to the half, obviously coming from the 1, and then we have a plus alpha. So that's the conclusion we reached. But maybe that's a view of it that's slightly more intuitive, less calculational, non-rigorous, unfortunately, but it perhaps a little bit more robust as a means of thinking about this if we start talking about other models that have trees, as the voter model, I think, will, if we talk about that. So I should say something about the proof. Prop 3 in the paper is the proposition that says that the process converges in finite dimensional distributions to the limiting process, which is the fractional Brownian motion with Hurst parameter half plus alpha. So I should say something about this in preparation for the talks we'll hear next time. We have a certain ally here in Gaussianity in the sense that there exists a unique stationary process which is the fractional Brownian motion of Hurst parameter alpha plus a half. I probably mean stationary increment process, I guess, in what I write here. Yeah, stationary increment process. Yeah, so what this means is, having got our hands on this kind of power from that lemma we proved, lemma 3.1, given this uniqueness and this growth rate for the variance of Sn, which is lemma 3.1, we're rarely down to proving Gaussianity. So what we've got is a situation, if we look at it at the level of the trees, we have one component that suggests Gaussianity, because what we want for Gaussianity is to have many contributions to variance independently coming without any one of them offering a macroscopic contribution to variance. So as n rises, the trees will contribute to the variance, but no one of them will make a significant 1% contribution as n rises. Each of them will sort of die away. So that's one component we need. The other component we need, though, is that at some level we want the total variance in the system to be a kind of a concentrated quantity. Actually, the discussion about the cookie collector problem points out this difference, because in the cookie collector problem, the local times are such that they each contribute a small amount, and there are many of them, but they have this correlation that prevents the total variance in the system being concentrated. So it's more like riding along on a Brownian motion and then jumping off at a random time, something that you have the perfect formation of Gaussianity at some level in the process, but your ability to jump off the process at a variable point is preventing the formation of a Gaussian statistic for you for that cookie collector problem. So those are the kinds of considerations that go into this. So the way we argued this in the paper was to take the notion of the process being built up from information, realizing information in the deep past, far to the left, and iteratively realizing that step by step and watching the concerned random variable Sn kind of form, given that conditional information. So we take M here, and so M will be, you can think of it at least at the beginning of the process as being highly negative. And then this is the information in the deep past, as it were. If N is highly negative, then this is the information strictly to the left of N, the plus and minus 1 decisions in that zone. So what I can do is each Xn, which is just a plus or minus 1 assignation that's made to a particular site N, what I can do is to define this object. So this object is, given the plus and minus decisions made in the past before level M, this is the conditional value of Xn given that information. So I suppose the formula is the mean and the conditional mean of Xn given this information here. So what we can do is, so we have something similar, just the same definition with obvious definition for this conditional mean here. So, all right, well, I can naturally regard that as this object. I mean, as I form, if I consider a given value Xn, I can see it as being formed as a kind of infinite sum from the past of information. It's something like this, you know, all the way back into a moment in the relatively deep past where I'm writing something like this. So if I look at this structure, then if I begin in the deep past, then I simply start realizing my process by forming it, by filling in the ancestral line piece by piece, and the deep past advances. Then at any given moment, I have an estimate for Xn, which is Xnm, where n is this index for the past. So that evolves as a martingale, making kind of fair, balanced movements upwards and downwards, and it converges to Xn. And in fact, there's no sense of Gaussianity here. Obviously, Xn is a plus or minus 1 after all, with Bernoulli distribution. So what happens in this process is that the last few steps are very significant. If you're just 10 steps back and you're talking about xn, n minus 10, there's significant uncertainty about the actual value of xn. It's as you creep in and sample, and gain information as you really approach n, you really gain, 27% of the information at the final step. It sort of builds up. So the individual moves are significant. But when we do the averaging in the definition of Sn, Sn can be written in a similar way, replacing x by s on this page. But then the individual difference of s conditionals that you see can be written as a, writing out the sums here and seeing this. What you're seeing, in other words, is intuitively what happens is in adding up to form S from 1 up to n, all the x values, and then coming in from the deep past at each stage, there won't be any given moment at which we gain a tremendous amount of information, because, well, if we're working in the significantly negative region, the individual x's won't change significantly. As we come into the positive region, what will happen is a phenomenon in which I advance by one step and I really make a significant contribution to understanding what the x values will be for the vertices that are very near the point, but they are dwarfed in number by the remaining x values that are of order n generically in this formation. It's a special situation as you reach the very end of the process, but then that itself is only making a small contribution to the actual variance involved. So this is kind of the idea of what's going on. Perhaps I can make a comment about, I can at least write down a formula for what happens in this evolution at a given moment of time. So if I'm concerned with the value here, and what I am doing is m is somewhere to the left, what's happening is I'm realizing a new bit here. This is becoming available because what I'm doing is at this moment, I'm, as it were, sampling the tree backwards and learning what this is, plus or minus 1, previously unknown. And then this difference I wrote represents that gain of information and the difference it makes to us. So what happens is, before we have that information, then if you're, as it were, sitting here, you ask yourself the question, what's happening? You don't know the value. All you can do is estimate it. You estimate it by by playing hopscotch one move and then taking the mean value. That's what this value is. Whereas after you realize it and you learn it's 1 or minus 1, then it's just what it is, and this is here. And then in terms of your overall, how much you care about all this sitting out here, well, for that, what you do is you form the line back, and then you care about this new piece of information only if you hit this level. So the probability of doing that is a qn minus m. That's our notation for that. So yeah, you have these kind of formulas. So you see, if you're worried about the, you have this kind of formation of a martingale, and then you have formulas like this. I just add up the formula I just wrote. I have a quantity we call fn m here, which is just a sum of q values that were just recorded in that formula. So we have these kind of formulas going on in the system. Yeah, okay, so, but the point to emphasize, one point to emphasize is that, what is the actual, I won't go through details of computations for this stage, but I will tell you the kind of result that needs to be proved. So here's an important quantity. If I take the information that is in the system to the left of, I think this is what this notation means, to the left of I, I think I'll write the formula down and then explain my understanding of it in words, I think. It's a bit picky to write. So my handwriting perhaps becomes slightly ragged. what's going on here is that the process is being formed from the deep past. And at each stage, a particular statistic that interests us, such as the value of SM, we have an estimate for it, conditional on this information further in the past. So at each stage, that statistic goes up or downwards a little bit, and it converges ultimately to SN. So the change made, if we square the change made from one step to the next in that conditional estimate, that is a conditional variance for the step given the past. So this statistic is a cumulative, it's a sum of the conditional variances coming from the past. So you can think of this as like riding along a Brownian motion in a certain sense and jumping off at a certain moment. Or at least it will be a Brownian motion if I have the condition that the individual contributions to variance that go on here are insignificant. So this should be a lot smaller than the overall contribution. The mean of the sum of the conditional variances should not receive any significant influence from any individual step. So the idea here is that this will be true for all terms I, with epsilon n being something that tends to 0 in n. Now we've got that for that cookie collector model though. The trees are, well, it's a slightly different view, but it's related to, it's a distinct but similar point that the trees or the local times don't dominate macroscopically the interval in question. So the other thing we need is this notion. This means that in some sense, this evolving thing is approximated by a Brownian motion, with the steps not really measuring individually. But we then jump off the Brownian motion at a certain point, and we have to do that at a clearly defined deterministic time if we're going to get a Gaussian statistic. So we need a concentration in the sum of the conditional means should concentrate with high probability near its mean value. Well, okay. I a little bit gave up on the notion of this detailed presentation at this point. You can look in the paper to see we have expressions for Vn in terms of quantities like the Fmn, the sums of the Q sequences, the contributions coming from the individual steps in the formation of the sum of the conditional variances. The summands, have expressions for them. Yeah, well, I mean, the reason, though, that you might expect, on the basis of the information we have, the reason that you may expect these two properties to hold it is that we have this kind of control on what the Q sequence is doing. We have this heavy tail environment in which we're unlikely to hit distant points with the hopscotch. And then these things point to, I think, the notion that in the formation of Sn, there's no individual step in the formation that makes a great deal of difference at the level of contribution to variance. So, well, yes, okay, that wasn't a terribly detailed discussion of the details of that, but rather a flavor of it. Let me stop here for today.